Okay, so you all, this is just a part 2 recording of chapter 4 that we did not get to finish in class that I promised you. So I'm going to start from here. We finished this slide, but I just wanted to back up a little bit to remind you all before we go into the next portion about the metabolic acids and buffers. So we've been talking about in this chapter pH, okay? And so we have to remember that our bodies are a chemical reaction, okay? And so when you look at all the metabolic activity that is produced, it's roughly about 22,000 milliequivalents of acid per day, okay? So if we were to dissolve all of that acid at one time, if it was not buffered, okay, so if there was no buffering system available, the pH would be less than or lower than 1. That is very acidic, right? So what happens is the pH, the various compartments of our body and the solutions that are within have certain parameters that the pH should be around. For an example, our blood is normally maintained between 7.36 to 7.44. An intracellular pH at about 7.1, or usually between 6.9 to 7.4. Right? And so until all of the acid that is produced from metabolism can be excreted out as CO2 in expired air, so through i.e. breathing, okay, or as ions in the urine, there needs to be a buffering that happens internally within our bodily fluid. So there has to be a way to buffer all of that to help with maintaining the pH. So the major buffer systems in our body are the bicarbonate, carbonic acid, which operates primarily in the ECF, the hemoglobin buffering system in red blood cells, the phosphate buffer system in all cells, and then you have the protein buffer system in the plasma, the cells and plasma. So let's talk about the bicarbonate buffer system. When you think about this bicarbonate buffering system, you have to think about the major form or source of metabolic acid in the body, and that is from CO2. And it's produced from fuel oxidation, okay? So the TCA cycle. So when you're under normal conditions, the body's going to generate more than 13 moles of CO2 per day. CO2 will dissolve in water, and then it will react with water once dissolved to produce carbonic acid. This is where we get the balance of the bicarbonate carbonic acid reaction, okay? And that reaction is accelerated by the enzyme carbonic anhydrase, okay? Now, what is carbonic acid? It's a weak acid that is partially dissolved into hydrogen ion and bicarbonate ion. So carbonic acid is both the major acid produced by the body and its own buffering system. Okay? When you think about carbonic acid, okay, its pKa itself is only 3.8. So that lets us know that it's not a very strong acid. Remember, the lower the pKa, the stronger the acid. So it's not a very strong acid. Okay, so when you talk about the blood pH of 7.4, it's almost completely disassociated, and therefore, or theoretically, it's unable to buffer and generate bicarbonate. So how does this relate back to the bicarbonate buffering system? Think about the dissolved CO2, okay? And according to, when you think about that whole process, carbonic acid can be replenished from the CO2 in bodily fluids and the air, because the concentration is going to be, the concentration of that dissolved CO2 in the body fluids is about 400 times greater than that of carbonic acid. So as you add a base, okay, as the base is added, and hydrogen ions are removed, you have that dissociation from carbonic acid. And the dissociation from that carbonic acid allows for a level of a balance, as you can say, okay? So that dissolved CO2 can react with water to replenish carbonic acid. And it's almost like this cycle. But we have to also think about the lungs. In the lungs, you have that dissolved CO2, and it's in equilibrium with the CO2 in the air just through the process of breathing. So the availability of CO2 can be modulated by the art of breathing. And we've talked about, and I mentioned this before, Kussmaul breathing. Go back to our patient that the new patient that you all were, well, he wasn't new, but the patient, Mr. Veer, okay, and dealing with his grandson, I believe, Dennis the Menace Veer. Because his grandson took all of those pills, he began to, he was nervous and he was hyperventilating, causing issues. So our art of breathing also has an impact on our pH in our body. So how does understanding this play a role in the calculating the bicarbonate buffering system and association with pH? So I want you to think about it from this perspective. The pKa, okay, for the bicarbonate buffer system in the body, combined with the Kh, which is that hydration constant for that reaction of water and CO2 to form carbonic acid, you can obtain, using those various components, you can obtain a modified version of the Henderson-Hasselbalch equation. And that's the equation that you see here, okay? So what do those various components mean? To use the terms for the blood components, it's often seen, which is measured in the emergency room. You have the dissolved CO2, which is expressed as a fraction of the partial pressure of CO2 in arterial blood, okay? And that's called PaCO, and that's what you see here. Okay, that is called PaCO. The pKa for dissociation of the bicarbonate anion is, and that's what you see. Oops, my apologies. Hold on. Sorry about that. The pKa for the dissociation of the bicarbonate ion HCO3, okay, here, into the hydrogen ion in that bicarbonate is 9.8. Therefore, you only get a trace amount of bicarbonate that will exist in bodily fluids. So the best way to estimate that is to use this equation here. And this is a standard. This 0.03 is a standard. See this portion right here, okay, is expressed as the milliequivalents per mil, and PaCO, which is right here, is expressed as mmHg, okay, and that is millimeters of mercury, okay, millimeters of mercury. All right, so I want you to read through this question, but go through this background. So read through this, and then I want you to think about and ask yourselves, why is this occurring? So it talks about Kussmaul breathing, okay? And this relates back to our patient diabetes, okay? So how does this relate back to diabetes, our patient? And remember all the things that we've learned about her up until this point. And then how does Kussmaul breathing, how is it associated with or affect the pH? Given the information that you have here, I want you to calculate her pH given that information. Now, what do we have? Well, in the emergency room, they took her or measured her partial pressure, which is PaCO. It's 28, okay, which we know is the millimeters of mercury. So you're going to take this measurement here, and you're also going to measure the bicarbonate level, okay? So you're going to take these two measurements here, and you're going to plug it into this equation here, okay? And everything else, all the numbers, the 6.1, the 0.03 are standard. So you'll plug in the values for the two measurements that were taken from diabetes to determine her pH. All right, so now let's get to the bicarbonate and hemoglobin in red blood cells. So this is another bicarbonate buffering system, okay? I want you to think about, we just talked about the CO2 from breathing, and that is produced from the metabolic activity. Now, one of the things that is different with the blood is that although there's no carbonic anhydrase that is found in blood plasma or even in the interstitial fluid, the red blood cells contain a high amount of the enzyme. And so CO2 is going to be able to be rapidly converted to carbonic acid within those cells. And that's what you're seeing happening in this diagram here. Okay. So as you have the carbonic acid dissociating, the hydrogen ions are going to be released as and buffered in combination with hemoglobin. So that side chain that you see of the amino acid histidine in hemoglobin has a pKa of 6.7, and so it's able to accept a proton. That bicarbonate anion is transported out of the red blood cells into the blood in exchange for chloride ions. And the bicarbonate is relatively high in the plasma. Okay, so as the red blood cells are approaching the lungs, the direction of the equilibrium is going to reverse. That's what you're seeing here. Okay, and this is specifically for muscles, but you would see that reverse that happens in the lungs. CO2 is then going to be released from the red blood cells, causing more carbonic acid to dissociate into CO2 and water, and more hydrogen ions to combine with bicarbonate to form carbonic acid. Hemoglobin loses some of its hydrogen ions, which allows for oxygen binding. And the bicarbonate buffer system is linked to the delivery of oxygen into the tissues. Okay, so ultimately, as the pH falls, individuals breathe more rapidly and expire more CO2. So this is connecting breathing and pH to the respiratory system. And we know that the respiratory system within the hypothalamus is helping to control the rate of breathing. And that the hypothalamus is sensitive to changes in pH. Okay, let me repeat that again. The pH, the hypothalamus is sensitive to pH. And so because of this connection, okay, as your pH falls, the individual is going to have a change or modulation in their breathing patterns. So as it becomes more acidic, you're going to breathe more to expire out CO2 to prevent the increase in the formation or the dissociation of carbonic acid. As the pH rises more and it becomes more basic, you're going to breathe more shallow. Okay, and so the rate of breathing contributes to the regulation of your pH, okay, and its effect on the dissolved CO2 in the blood. So this is really, really important in understanding how our breathing patterns help regulate our pH internally, just naturally. Okay, and so looking at this diagram here, you can see that as CO2 enters the blood, it combines with water to form carbonic acid. Okay, as the red blood cells contain high amounts of that enzyme, the hydrogen ions in the blood bond to the phosphates, as you see here. And so this is ultimately a type of, it's the buffering system within itself. Now, another component that you see here, right, is the ketone body, acetoacetic acid. Okay, you see acetoacetic acid. Now, how is this acetoacetic acid involved in this process? I want you to think about the phosphate anions and proteins that are part of major buffering systems as well. They're involved in maintaining a constant pH. So even if you look here, you have the inorganic phosphate anion H2PO4, what you see right here. H2PO4. And it has a pKa. It disassociates, and its disassociation generates hydrogen ions and the conjugate base HPO4, which you see here, okay, and here. And that has a pKa of 7.2. So phosphate anions play a major role as an intracellular buffer in the red blood cell and in other cells as well, where their concentration is much higher than in the blood and the interstitial fluid. And this is what you're seeing happening in this diagram here. There's a high amount of content of proteins that contain histidine and other amino acids that can accept protons in a fashion similar to that of hemoglobin. And so this is helpful in maintaining the pH. Okay, so the transport in and out of hydrogen ions out of the cell is important for maintaining that intracellular pH. Another component that we have to strongly consider when we talk about intracellular pH, that metabolism is going to produce several other acids in addition to CO2. You have the acetoacetic acid, the beta-hydroxybutyric acid, which are those ketone bodies, and they are produced from fatty acid oxidation, okay, to ketone bodies. You also have lactic acid that is from glycolysis in muscles and other tissue. The ketone bodies for these other metabolic acids like carboxylic acid is less than 5. So these other acids completely dissociate at the pH of blood and cellular fluid. So what happens is if you have that issue where you have the dissociation, if the cell becomes too acidic, more hydrogen ions are going to be transported out of the cell for another type of ion, and it can, in this case, sodium ions, okay? And it's a way to help balance the flow of these ions so that you don't have a high acidic environment within the cell or intracellularly. If the cell conversely becomes more alkaline, then more bicarbonate is going to be transported out in exchange for chloride ions. So there is a clear connection, right, between the transportation, the import and export of hydrogen ions and chloride ions to have a balance or to maintain a equilibrium of the buffer, the pH in the cell, okay? Metabolic anions are going to be transported out of the cell together with the hydrogen ions, because the whole point is, as you are transporting out these anions, you want to make sure that you're keeping a balance of the pH. Now, when it comes to other components like your urinary hydrogen, ammonium, and phosphate ions, you have something called what is the non-volatile acid that is produced from body metabolism that cannot be excreted as expired CO2. So breathing is not going to help with the excretion of these components that aid in modulating the pH, okay? And so therefore it has to be excreted in urine. Most of that acid, hydrogen ion, is excreted in as undissociated acid that generally will buffer in urinary pH between 5.5 to 7. As the pH of 5 is the minimum urinary pH, the acid excretion includes inorganic acids such as phosphate, ammonium ions, as well as uric acid, dicarboxylic acid, and the TCA such as citric acid. One of the main sources of non-volatile acid in the body is sulfuric acid. Now, sulfuric acid is generated from sulfate-containing compounds that you ingest in your diet from foods, and they are used to metabolize sulfur-containing or to produce sulfur-containing amino acids like cysteine and methionine. It is a strong acid that is dissociated into hydrogen ions and sulfate anion in the blood and in the urine. Urinary excretion of it helps to produce or helps to remove, acids. To maintain a metabolic homeostasis, you have to excrete the same amount of phosphate in the urine that you ingest in food as phosphate anions and organic phosphates such as phospholipids. They have to be excreted in equal portions, okay, to help maintain that balance or homeostasis. Whether that phosphate is present in the urine as H2PO4 or HPO4, it depends on the urinary pH and the pH of the blood. Ammonium ions are major contributors to buffering urinary pH, but not blood pH. Ammonium is a base that combines with protons to produce ammonium. Okay, so ammonia combines with a base to produce ammonium ions. It's a reaction that occurs with a pKa of 9.25. And what do we learn about pKa? The lower the pKa, the stronger the acid. And so in this case, it is not a strong acid, okay? It is not a strong acid. Now, even though it's not a strong acid, it has to be kept at a low concentration because it is toxic to neural tissue. So despite it not being a strong acid, the aggregation or accumulation of this can cause degradation and toxicity to neural tissue. The kidneys are going to generate NH4 and excrete it into the urine in proportion to the acidity or the protein concentration of the blood. So as you have renal tubular cells transport hydrogen ions into the urine, they're going to return it right back as bicarbonate anions into the blood. So there is ultimately this cycle that helps to provide a balance. So this diagram is pretty interesting, and I want you all to take the time to read it because it helps you to understand, truly understand body fluid homeostasis, okay? So here you have figure 4.10, and it talks about water gain versus water loss. And this often comes into play in effect when it comes to like even blood pressure, okay? So body fluid homeostasis, which is a constant body water balance. Your intake is influenced by the availability of the fluids in blood and food, thirst, hunger, your ability to swallow. This also is associated with the rates of breathing and evaporation, and urinary volume will also influence water loss. The body adjusts the volume of urinary excretion to compensate for variations in other types of water loss for variation intake. The hormones, aldosterone and antidiuretic hormone, ADH, help to monitor blood volume and osmolality through mechanisms regulating thirst and sodium and water balance. So ultimately, diuretics, okay, our antidiuretics or diuretics help with monitoring fluid levels. So whether you gain water or retain water will also affect pH. Hydrochloric acid, okay? So briefly just tapping into hydrochloric acid is also known as gastric acid, and it is secreted by parietal cells in the stomach, okay? And they are in the stomach lumen where you have a strong acidity and it denatures ingested protein. So this is how when we're eating food, a lot of our proteins are denatured so that they can be degraded by digestive enzymes. When the stomach contents are released into the lumen of the small intestines, you have gastric acid that is neutralized, by the bicarbonate, and it's secreted by the pancreatic cells and by the cells in the intestinal lining. So hydrochloric acid is a very acidic acid, and it's helpful in the denaturation of ingested protein. So this strong acid in the stomach is important for digestion of enzymes. As we begin to wrap up this chapter, I want you to take the time. I won't do it in this video recording, but I want you to go back and look at the clinical comments for diabetes. Okay, I want you to pay attention to some of the concepts here that I want to kind of point out to you. So in the reading, it talks about insulin administration. Okay, so look at the compensatory mechanisms that are involved with pH and causing acidosis. I also want you to think about how CO2 expiration plays a role in that, and what role does respiration overall have in pH. Go back through Mr. Veer, Dennis, and Mr. Percy Veer. Also pay attention to behavioral systems, right? Because our behavior also plays a role in metabolic activity. Why? Physiologically, some of our behavioral issues can trigger or stimulate internal modulations of pH, like anxiety, for an example, can alter one's breathing pattern. And we've already identified in this chapter that breathing is associated with as a buffering system, or part of the buffering system to help regulate pH. So anxiety and high stress can also affect those things by altering indirectly our pH through modulation or change in breathing patterns. All right. And then I want you to look at the biochemical comment. So your book does a great job of showing you the correlation between the clinical aspects and then the biochemical aspects. So we've talked about the diuretics, the antidiuretics, which is associated with water retention and water loss. So I want you to think about how this plays out chemically, biochemically, what is happening in our patients that are either retaining water or losing water. And what is this associated with? What disorders is associated with? What is happening chemically? Okay, and it's going to lead you again back to those antidiuretic hormones. All right, so this is the end of chapter 4, and I hope that you have learned something that you can apply to your upcoming written case studies and your oral case studies on tomorrow evening.